Hello, happy December 15th. Today I want to talk about the other side of CP violation. So this is something I've already mentioned a few times, and CP violation is what gives us the matter-antimatter asymmetry in the universe. Now, our theories are built in a consistent framework known as CPT, and that stands for charge conjugation, parity, and time reversal. And the idea is if you perform a CPT transformation, you can't tell the difference between before and after. So let's say we have an electron moving forwards in time. If I swap the electron for a positron, so I give it a positive charge and it spin flips, and then I move time backwards, you can't tell whether that was actually an electron moving forwards in time or a positron moving backwards in time. There's no measurement that you can make that will be able to tell the difference between those two scenarios. And that is the basic assumption of quantum field theory, our best model of the universe. Now, if the CPT theorem is incorrect, then all kinds of crazy things happen. For example, we no longer have causality, so time can go forwards and backwards and weird things can happen. You can end up with a particle being in two places at once, and it stays in two places at once even when you try to measure the thing. So it's not weirdness in the sense that quantum mechanics is weird, it's inconsistency. It's so weird that there's no consistent way of describing it or explaining it. So CPT is a fundamental theorem for us. Now, you might be thinking, well, we've already violated CP, that's what the CKM matrix is all about, that's why we have more matter than antimatter. Doesn't that mean we also violate T, or time? And that is what this video is about. The answer is yes, we violate time. Time has a preferred direction, it goes forwards rather than backwards. And when you measure CP violation, you indirectly measure time violation. Now, one of the really cool results to come out of the bar experiment this year is a confirmation of time violation. It was a very, very complicated and very difficult measurement to make because they had to consider all these different final states of B mesons, and reconstructing B mesons is extremely difficult, even when you have an excellent detector like bar, and even when you know your centre of mass energy. So the fact that they can put out this measurement to me is just fantastic. It's unambiguous evidence that T violation takes place, and you don't have to measure C and P violation to actually see this. Now, in a situation where you have CP and T violation taking place at the same time, that means that you then have to untangle them all because they're all equivalent to each other. You have to subtract the CP contribution to see just the T contribution, or the other way around, or you have to measure a combination of all of these things. No, what bar did was they separated out the T violating part, and it came out spot on what they expected, given that they'd already measured CP elsewhere. And to me, that is one of the coolest results of the year. Anyway, I'll link to the papers in the description of the video, so check it out if you want to know more, ask questions. It's a really cool result, and I'll see you tomorrow.
After making this video, I decided that the summary needed a bit more attention because this result is so beautiful, so here are the main points. In summary, we have measured T-violating parameters in the time evolution of neutral B mesons by comparing the probabilities of various transitions to their T conjugate. We determined the main T-violating parameters and observed directly for the first time a departure from T invariance in the B system with a significance equivalent to 14 sigma. Our results are consistent with current CP violating measurements obtained invoking CPT invariance. They constitute the first observation of T violation in any system through the exchange of initial and final states and transitions that can only be connected by a T-symmetry transformation.